It's a pleasure for me to present today the third chapter of the book of Professor Paul Godwin on understanding the bias and accuracy measures of the forecasting software. So in this presentation, I'm going to start by the definition of the bias and the accuracy. What's bias, what's accuracy, what's the difference between these two concepts. After, I will talk about fitting and forecasting, what's the difference between in-sample and out-of-sample periods. I will talk also about how to evaluate forecast accuracy, the two ways to do that, and I will go after to present the bias measures and the accuracy measures which are frequently used in forecasting softwares. And at the end of the presentation, maybe I will tackle two interesting points that were discussed in the book about exception reporting and the forecast value added analysis. So let's start with the definition of bias and accuracy. So bias in forecasts refers to a persistent tendency for the forecast to be too high or too low. I tried here to generate some examples. As you can see in the first graph, we have the actual sales in red and we have the forecasts in blue. And the forecasts here are always lower than the actual sales. So here we said that, we have biased forecasts. Here there is a clear bias in our forecasts. But in the second example, which is we have the same actual sales, but we have different forecasts. And now you can see that the forecasts sometimes are higher, lower than the actual sales. But maybe when we calculate, the average of the difference between the sales and the forecast, we will find something which is near to zero. So we call this unbiased forecasts. And we will see after how to measure the bias in forecasts, but I think these two examples show clearly what's biased forecast and unbiased forecast. And of course, you can imagine the situation where forecasts are higher than the sales, and in the situation also we will say that we have biased forecasts. For accuracy, so accuracy represents the typical closeness of the forecast to the actual sales. Here, for example, you see in the red line the sales, the actual sales, and in the blue line the forecast. And you can see that the forecasts are far from the sales. There is a difference between the forecast and the sale. And here, it's clear that we have inaccurate forecasts and there is a problem with the accuracy. But in the second example, you see that we have somehow accurate forecasts because the forecasts are very, very near to the sales. We'll see after how to measure the accuracy, how to say that we have good forecasts or bad forecasts. But just there's an important point which has been discussed in the last presentation by the Professor Paul Godwin. You know that when we observe the past sales, we will see that there are patterns like the seasonality and the trend, and there is noise. And noise is something that we cannot predict in the future. So it's sure that there will be always a difference between the forecasts and the actual sales, and there will be always an error because there is the noise part which we cannot predict. And some sales history consists largely of noise, so we will expect to have large differences between the forecasts and the sales. As I said before, forecasting methods are not intended to anticipate noise. So we want just to anticipate the patterns we observed in the past. Noise is something we cannot anticipate. If we anticipate noise, it means that maybe we are overfitting. So let's talk now about what does fitting mean and what does forecasting mean also. So when we measure the accuracy of a forecasting method, it's important to distinguish between the fit and the true forecasting of a method. Because if you try to forecast what you observed in the past, this is called the fit. So I will show this after with a graph and it will be more clear. So yeah, maybe you can see it here. You can see the data in blue, it's the sales with the blue points. And the red points represent the fitted values. So here what has happened? We wanted to forecast this part. So we used this data. And of course, yeah, we can have forecasts also for this part. And these forecasts are called fitted values. They are not true forecasts. Why we call them fitted values and not true forecasts? Because here in this part, the true values of sales were used to fit the model or the method. So yeah, they are somehow biased and they cannot tell us about the accuracy of the method or the model we are using. So this is an important point. To truly test a forecasting method, yeah, we should hide some of our sales data from it and see how it will forecast sales that it hasn't seen. Yeah, this is what we see here. It means if you want to see the strength of your forecasting method or the accuracy of your forecasting method, you should hide part of the data, which we did here, and use just this part to fit your model and after to predict. And to test your forecasting method, you will compare here your forecasts to the sales, to the actual sales. Yeah, people call the periods used to fit the model the in-sample periods, and the periods used to test the model, the hold-out sample or the out of sample periods, or sometimes we call it the test set, and we call this part the training set. It's important that when we want to evaluate the accuracy of a forecasting method, we have to use the hold-out sample, the periods that were not used to fit the model, but the periods we kept only to evaluate the accuracy of the model. Here I think it's an important point. You can see, so here we have in the black points, we have the observed, the actual sales, and you can see that we can always find a model that fits well the data. Here, for example, we are using polynomial model and we are increasing the degree of the model. You see when the degree increases, the model in blue, fits well the data, but see what happened here after the fitted values. You see that if you mark, for example, when the degree is 15, it's clearly that our model will not fit well, will not do good forecast. Even if it fits well the data, it will not be, it will not have a good forecasting accuracy. So this is what we call overfitting, because here we didn't fit the patterns of the data, we fitted also the noise. So this is overfitting, and when we have overfitting, it means that we will have a poor predictability of our method or our model. So this is an important point to keep in mind. It's always possible to find forecasting model that perfectly fits sales in the simple period, but it's not always a good forecasting model. Now we will see how to evaluate for the forecasting model, and there are two, let's say, big approaches. The first one is the fixed origin evaluations, and the second one is the rolling origin evaluation. So let's start with the first one. Here, to evaluate our forecasts, we will divide the data into two sets, the in-sample periods and the holdouts periods. And all the forecasts, for example, here we said that we will use from the first week until the the week number 40 as in-sample periods, and we will use all this data to forecast our demand in the future. And here, yeah, we have a fixed origin, which is the week number 40, because we will start to do forecasts from the week number 40. So we'll have a forecast for the week 41, 42, till week 50. But this way has limits. Yeah, the first is that we will have one forecast for each lead time. What we mean by lead time, it means, for example, here you are at week 40, and the forecast, yeah, we have for week 41 is a forecast with lead time of one period, because yeah, between 41 and 40 there is one period. So we say that we are having a forecast for a lead time of one period. We will, with the fixed origin evaluation, we will have only one value for the one period ahead forecast. We will also have only one value for the two periods ahead forecast, and one also value for the 10 periods ahead forecast. So it's not, maybe statistically speaking, a good way to estimate the accuracy of forecasts. Yeah, the second point is that many forecasting softwares which use the fixed origin evaluations, they will give you the average or the mean accuracy over here the 10 weeks. So for example, if we say that the accuracy for one period ahead is good, and after, yeah, the accuracy for 10 periods ahead, yeah, logically it will be lower than the one period ahead, because we are far ahead in the future, and it's more difficult to predict the future when the lead time increases. And yeah, with the fixed origin evaluation, we will calculate the average of all these periods, even if they are different and their accuracies are very different. So maybe we will have a biased estimation of the accuracy, and it's not the best way to do that. And after,
can I say something here?
Yeah.
I just want to mention that some of the methods, the more simple methods, like simple exponential smoothing or a simple moving average, would provide the same exact forecast for all of those 10 periods. Which make it even also kind of weirder. I mean, if you look at the graph of a simple method, then you have a straight line going from 40 to 50, which clearly shows like it's not a very,
flat forecasts.
Way to do it. Yeah. Okay. Sorry.
Yeah, exactly. Yeah. Thanks, Thanos. Yeah. This is, I think, an important point. Some methods provide the same forecast for all the periods ahead. So, and it's sure that the 10 periods ahead will be a bad forecast. So, yeah, with the fixed origin evaluations, this will be a bias to estimate our accuracy. And after, also, the third point is that sometimes, maybe we don't have this case here, but imagine that at week 40, something weird will happen in the sales. So this will badly influence your estimation. It will not be a true estimation, because by chance you are evaluating your forecast on the, let's say, the worst period. So yeah, using a fixed origin evaluation maybe is not the best way to evaluate forecast accuracy, and there is a solution to handle the limits of the fixed origin, which is the second way of doing evaluation, called the rolling origin of evaluation, and we will explain it now. So here, the principle is simple. We will start like the fixed origin evaluation. For example, here we will start with the origin week 40, and we will record the accuracy of forecast for weeks 41 to 50. But we will not stop here. We will move to the origin we will move the origin to week 41, and we will record the accuracy of forecast for weeks 42 to 50. And we will repeat the same thing until we arrive to week 41. And here, we can generate only the forecast for week 40, and we can record the accuracy of this forecast. So you can see it here, where when the origin was week 40, we were able to generate forecast for 41, 42 until week 50. And we were able also to measure the accuracy of this forecast. At 41, we cannot do it for 41, so we will start from 42, and we will repeat the same process until week 49. And here, PA means periods ahead. Here, you have one period ahead, which means you have lead time of one period. Here, 2 periods ahead, which means lead time of 2 periods, etc. But you can see here that now we have 10 one period ahead forecasts. It means we have 10 values for the accuracy of 1 period ahead forecasts. And after we have 9 for the 2 period ahead forecasts, 7, 8, 7 until we have only 1 value for the 10 ahead forecasts, 10 periods ahead forecasts. And here, you have to be careful when you evaluate the accuracy, because as you see, for 10 period ahead forecast, you have only 1 value. So the estimate of the likely accuracy of forecast for this lead time has to be treated with caution. You have to be careful for this period, because when you have only 1 value, it doesn't estimate well the real accuracy. Okay, so I hope that it's clear. And now for the difference between fixed origin evaluations and rolling origin evaluations. So we will see some rules, some, let's say, guidelines, how to split your data into in-sample and hold-out sample. Generally, and as mentioned in the book, the decision is a judgment call. But there are some guidelines. First, and which is the most important thing, is that usually when you want to do forecasting, you will use your forecast to take a decision. Let's say, for example, in your inventory control. And for example, if you are doing this for inventory control, you know that, you need forecast for 1 week. So if you want to evaluate the accuracy of your forecast, you need at least 1 week in your hold-out sample. And after, you have to decide how many values you need to have for 1 week ahead forecast. And so let's call the lead time L, and let's call the number of values you want to have for this 1 week ahead forecast A. And the size of your out of sample or hold out sample will be L plus A minus 1. Maybe with an example, it will be simple. So suppose you are forecasting 12 months ahead, but think that you need 6 forecasts at this lead time to get reliable indication of a method's accuracy. So here your lead time would be 12. You need 6 values of 12 ahead forecasts. So as an out of sample or a hold out sample, you need 17 periods to be able to do this. To be able to have 6 possible values for your 12 periods ahead forecast, you need 17 out of sample periods. Let's talk now about the bias measures. We talked about the bias and accuracy. Let's say how we can measure them and compare between these measures for different methods. So for the bias measures, there are 2 most used measures. The first one is the mean error, and the second one is the mean percentage error. We will see what's the difference between the 2 and how to calculate each one. So here, I took also the same example from the book, and we'll use it many times for the next slides. So here we have sales for 15 weeks, and we have one period ahead forecast. So here you have your sales, and here you have one period ahead forecast. So here you can imagine that we are in the holdout sample, and you have 15 weeks in this side, and you have one period ahead, 15 also one period ahead forecasts. Of course, the same rules apply also to the in-sample periods. So what's the error in forecasting? The error is just the difference between the actual sale and the forecast. So you can see here in the first week, it's 112 minus 85, which gives 27. I will talk after about the percentage error. And here you can see that when you have a positive error, it means that your forecast is too low. When if you have a positive error, it means that your actual sales are higher than your forecast. So your forecast is low, and you have to be careful about that. And a negative error indicates the opposite, that your forecast is high. So what's the mean error? The mean error is just the average of the errors. So it's the sum of errors divided by the number of forecasts. It means 15, and here we have 10.1 units. So how to read this data? You remember that we said when the error is positive, it indicates that our forecast is too low. So here in average, our error is 10.1 units, which means that in average we are 10.1 units lower than the actual sales. So this is something we have to improve. So as I said before, the mean error is positive, and it suggests that there is a tendency to under forecast sales. When our method is unbiased, it means when we don't have a bias in our forecasts, we would expect that in the long run, the mean error will be 0. It means we can sometimes under forecast, we can in some periods also over forecast, but in the long run, the mean error will be 0. So in this case, we will say that there is no bias in our forecasts. Of course, when we say in the long run, we need to have a big number of periods. Here we have 15, so it's a little bit difficult to have a mean error near to 0. The mean percentage error is somehow similar. We will just calculate the average percentage error, but let's see how to calculate the percentage error. So I will come back to this slide. So the percentage error is just the error divided by the actual sales. So it's 27 divided by 112, and we will have 24.1%. And yeah, we calculate this for all the periods, and after we calculate the mean, and we will find a mean percentage error of 4.1%. Percentage error is very useful when we want an assessment of the seriousness of an error, because you see here we have we have a mean error of 10.1 units, but we don't know, is it bad, very bad? Yeah, to know this, we should compare it to the real actual sales, because mean error of 10.1 when you have sales in average of let's say 100, and or you have sales in average of 1,000, it's not the same thing. So to measure the seriousness of your error, you should use the mean percentage error, which will give you here, for example, it's 4.1, which maybe you can say it's somehow good. And after there is an important remark here. We need to be careful when we use measures based on percentage errors, because if the sales here are very low, so it's sure that you will have a high percentage. Imagine that here you have sales equal to 4, and you found the forecast equal to 6, so you will have an error of -2, and your percentage will be -50%, which is a very high percentage. And you have this high percentage because you have a very low value of demand. And also we have to be careful, when we have zero demand, especially in intermittent demand. This measure maybe cannot be used. So we have to be careful with this situation. Okay, so these are the two famous, maybe most used bias measures. Let's now talk about accuracy measures. And here there are 3 families or 3 types of accuracy measures. The direct accuracy measures. Here I made a mistake. So we have the percentage accuracy measures, and we have the relative accuracy measures. We will see them after. So let's start with the direct accuracy measure. So first we have to see that the mean error, which measures the bias of forecasts, cannot measure the accuracy of forecasts. See this example. When 2 consecutive errors are, for example, +2,000 and -2,000. Here the mean error is 0, so there is no bias in the forecast, but the forecasts are not accurate. The forecasts here are not good because you are 2,000 units higher than the actual sales, and here lower than the actual sales, and here higher than the actual sales. So it's sure that your forecasts are not good, even if the mean error is 0. So we need another kind of measure. We need to handle the sign of the error, because the sign of the error is causing problems here to measure the accuracy. So what people use to handle the sign of the error, they use the absolute value of the error, and we have this measure, the mean absolute error, which is just the sum of absolute errors divided by the number of forecasts. We have also the mean squared error, which is the sum of the squared errors divided by the number of forecasts. And we have also the root mean squared error, which is just the square root of the second measure. We will see by an example how we calculate them and what's the difference between the 3 measures. So here, for the same example I used before, here I took the absolute values of errors and the squared values of errors. So when we take the absolute, so all the values will be positive, and here we calculate the mean error, we calculate the sum, we divide it by 15, and we find 24.3 units. The mean squared error here, in the same way, we calculate the sum of the squared errors, we divide it by 15. Be careful here, in the mean absolute error, the unit is units. It means, if we have, let's say, bottles of water, so the unit will be bottles of water, but here the unit is squared and bottles of water. It doesn't have maybe a meaning, and for that reason people use the root mean squared error. Even if maybe we will not see it in this presentation today, but from a mathematical point of view, this indicator is very interesting because it will allow us to do many things. Okay, so this is the direct accuracy measures, the most used direct accuracy measures. There are also the percentage accuracy measures. So here, with the same remark as we talked about the mean, if you remember the mean error and the mean percentage error, we said that when we see the mean error, we don't know that is it that bad, or we need a percentage to know what's the seriousness of our error. So here, also percentage accuracy measures are designed to reflect the seriousness of errors, by expressing the typical error as a percentage of actual or typical sales. And here, the percentage errors are what we call scale-free because there is no unit. It's a percentage. So you can compare between many products. It means, you can compare between the accuracy of forecast for your water and for your chocolate, for your bread. It's a scale-free, it's a percentage. Here's some of the measures I will present briefly today. So we have the first one, the mean absolute percentage error, maybe the most used one in forecasting softwares. Yes, it's a well-known measure, and after we have the median absolute percentage error, less used than the first one, but it can handle some problems. You have also the symmetric mean absolute percentage error, and we have the ratio of the mean absolute deviation divided by the mean sales. Okay, so I will present briefly, I think, the first three. So here the mean absolute percentage error is, you remember before we calculated the error, the percentage error. So here we will calculate also the absolute percentage error. We will just take the absolute value of the percentage error and we will take the average. And in our case, it's 23.7. And here we have a problem because, in any case, you have to be careful when you use this indicator, because when you have low sales values or zero sales, your percentages cannot be calculated or will be very high. Like this, it will make your this measure biased. So to handle this problem, maybe there is what we call, especially when we have low sales, there is this interesting measure called the median absolute percentage error. And here, I took the same example from given in the book. So you can see here are the different absolute percentage errors calculated in a sample of 7 weeks. So here we have 7 values, but you can see we have 5%, 40%, 14%, 3, 1, 9, and 1,004. So if you calculate the average of this absolute percentage errors, you will have a very high value, and it will be biased because one of the weeks has a high percentage, absolute percentage error. So your MAPE, this indicator will be very high. So way to handle this problem is to use the median absolute percentage error. How to find the median? You have just to do ranking to order this absolute percentage error from the lower to the higher, and after you have to take the median, which is the middle value of your periods. And in our case, it's 5. You can see from 1, 3, 4, 5, 9, 14, and 1000, and in the middle we have 5. So here, the median absolute percentage error, is 5%. In contrast, the mean absolute percentage error, the measure I presented before, is 148%. Yeah, this is a very bad. When you have this value, it means that your accuracy is very bad. But here, this measure is biased by just 1000. So yeah, we have to be careful. If we apply this approach, the median absolute percentage error, to the example I presented before, we will have 23.8%, which is similar to the mean absolute percentage error. Let's present another accuracy measure, percentage accuracy measure, called the symmetric mean absolute percentage error, and which is used to handle the problem of low sales and zero sales. So we said that this is a limit or limitation for the calculation of the mean absolute percentage error, the MAP, and this measure allows to handle this limitation. So here what you will do, first, you take the average of the forecast and the actual sales. It means you have your actual sales, you have your forecasts. Just calculate the average of the two values. For example, here we have 98.5, which is the average. Sorry, I have to go back. Just to show you. It was the average of 112 and 85. Okay, so I was here, and after you have always your absolute error. So you instead of dividing the absolute error by the actual sales, you have to divide it by this average. So here you have 27.4% for the first week, and you do the same thing for the other weeks, and you will find the SMAPE equals to 24.1%. And as I said, this measure allows to handle the problem of zero and low values of sales. But it has a problem. They said that it's symmetric, but it's not that symmetric, because I don't think that I have time to explain this, but maybe you can find the details in the book. But to wrap up, when you have low forecasts, when you have low average, or let's say low sales, your symmetric absolute error will be low, and when you have high, it will be high, and when you have high average, your absolute error will be low. So it's not that symmetric. When we use the percentage accuracy measures, we have to be careful because of the problem of the trend and the seasonal pattern. Because when there is a trend, for example, there is an upward trend, which means that your sales are increasing. It means that, because the sales are increasing, and you remember that the percentage error we divide by the sales. So this will tend to make the percentage accuracy measures smaller over time, and this will make our measures biased. And the reverse is true when we have a downward trend. It means when your sales are decreasing, your percentage measures will become higher over time, bigger over time, and this also will make your forecasts, your accuracy biased. And similar, when you have a seasonal pattern, for example, lower sales in the winter and higher sales in the summer. For the winter, we will have a high percentage errors, and the opposite in the summer. So we have to be careful of that. To handle also this problem, the relative accuracy measures are designed to allow us to compare the accuracy of a method against the benchmark of a simple competitor. So here what we will do, we'll calculate the forecast by our chosen method, and we will calculate also the forecast given by a simple method, and we will compare the two. For that reason, we call it relative accuracy measures. Usually, the simple competitor or the benchmark is the naive method. The naive method is the simplest forecasting method. The forecast for the next week is just the actual sale of the last week. So it's the most simple method. And the relative accuracy measures are scale-free. It means there is no unit, there is no scale in as like the percentage accuracy measures. So here, we will talk about maybe three. I think I will present the second because the first one is not that used. The second one is very famous. I think it was developed by Rob Hindman. And I will talk quickly about the third one. I think I will go quickly to the mean absolute scaled error. So here, which the MASE is found only by dividing the mean absolute error of our forecasting method and the mean absolute error of the naive forecast. It means given by the benchmark. So for our chosen method, we have a mean absolute error of 24.1, and for the naive forecast, it's 25.5. So the MASE is 0.94, which means that our forecasts are slightly better than the naive forecast. You see, because our mean absolute error is not that far from, it's better, but it's not that far from the naive forecasts. Okay, so the mean absolute error has two advantages. First, it can be used when we have trend or seasonal pattern, and it can be used also when demand is intermittent. But just be careful, because when you have an intermittent demand, usually the naive forecast in the out of sample periods can be zero, because you don't have a lot of periods in this in the hold out sample, and you risk to have naive forecast zero. So usually people, what they do, they use the mean absolute error of the in sample side. And after we have the Bayesian information criterion. I prefer maybe to I think I can present it quickly. So here it's a criterion used to avoid the danger of overfitting. So this is the idea. By how to do this, it's just by rewarding a method that has low mean squared error while also penalizing it depending on how complex it is. It means, if a method has a good or low mean squared error, you will reward this method, but if it's complex, you will penalize it, and you will find the best trade-off and compare the methods based on that. Here, maybe it's a summary of the accuracy measures I presented before. I will talk quickly about the exception reporting and the forecast value added analysis. So here, usually when we do forecasting, we don't forecast only the sales of one product, but we do it for hundreds or thousands of products, and it's very difficult to follow the accuracy of each product and see what are the problems. So people, the challenge is that it takes time and effort to check the forecast accuracy for each product. So many software or some software solutions provide what they call an exception reporting that alerts you when the forecast for a particular product may need your attention. How they do that? Yeah, the idea is simple. Yeah, they can, for example, set an acceptable range for error measures, such as the mean absolute error or the mean absolute percentage error, or they can alert you if you are your forecast for a specific period is exceptionally different than what usually happens in the past. So this is the idea of exception reporting. And after the forecast value add analysis, it's an extension of the relative percentage errors idea. It was proposed by a researcher from the SAS Institute. Here, instead of applying the relative percentage error, just one time, this researcher proposed to apply it for all the process for the forecasting. I will give you maybe the example here. For example, sales forecasting process in a company involves the following steps. So first, your computer produces the forecast, and after, sales manager uses judgment to adjust the forecast, and after, the senior manager also will adjust the forecast. So you have 3 updates for your forecast, and you would like to see what's the value added by each step. So first, what you will do, you will compare your computer forecast to your naive forecast. For example, here you see that the mean absolute percentage error was 32%, but your computer was 21%. So you won 11 points. And after here, also you improved by 2 points, by 2%. But with the senior manager, his or her value added analysis is minus 5%. So this is the idea of the forecast value added analysis. So to conclude, the performance of forecasting method should be assessed by comparing its forecast to sales that it has not seen. This is what I explained at the beginning of the presentation, what we call the holdout sample. And be aware of the dangers of overfitting. We can predict only the patterns. We don't fit the noise. It's important to measure the bias and the accuracy in our forecasts. And it's good also to use more than one measure to compare and to avoid bias in the measures. Be careful when you have low values of sales or where 0 values, like in the case of intermediate and demand. And forecast value added analysis can be useful in identifying which aspects of the forecasting process are improving your forecasting or are damaging it. So thank you for your attention, and please, if you have questions, don't hesitate to discuss or to write them in the Slack section. Thank you.
Thank you very much for the presentation.
The first question is that, would we ever correct a model by subtracting the mean error to remove the bias? Yes, in fact. Yes, the idea was not discussed in this book, but if you go to another book, which maybe we'll read in the month of October, you will find this idea. Yes, it's we do it in what we call residual analysis. Yes, if you have a bias, you can remove it directly from your forecast, and like this, you will have a correct, let's say, unbiased forecast. So I totally agree, Michael. I don't know if someone has.
I mean, it would be the case if you have if I am to say my thoughts on this. If you have somehow a model that consistently produces a biased model forecast, so it's consistently, let's say, 10 below the actual. But I mean, then you could just add 10. And then get a much better forecast. But it would be strange, to say the least, to have a model that would consistently be biased in the same manner.
I see your point, Thomas. I think you would wonder first why I get 10, because you will try to understand why you had this value. But as let's say,
so maybe there's a trend, and your model cannot capture the trend. Something like this might happen. So in that sense, having a bias is more of an indicator to look a little bit deeper, and then maybe in some cases, then you could just go and add whatever and then get a better forecast. But in general, it indicates that maybe you have a model that's not enough to capture the information that's there.
Yeah, I see. Okay, I don't know if it's a clear answer for you, Michael, or... Okay, I will take the assumption that it's clear. Okay, I see also another interesting and maybe difficult question by Chris. Yeah, you mentioned forecasting thousands of products. Do people use multiple models across the product range, and how they automatically apply different models to different products? Okay, so for example, if we are using exponential smoothing, I don't know if you, Chris, you are used to use this method. Yeah, you may apply exponential smoothing for each product, and it means for each product you will have its own model.
Yeah. So, but what I mean is, do people use like exponential smoothing and something else as well? And some, that's more what I was wondering, because I'm sort of looking at, I want to forecast lots of drug uses, loads and loads and loads of drugs, you see. And my concern is that, say, exponential smoothing would work with one set of drugs, but not with another one. And I want to be able to switch in and out of different types of models, but like thousands. And I wondered if, people did that and how they, what the method was.
Okay, I see. Yeah, okay. Sorry, I think I thought that you were talking about other thing. I thought that you were talking about fitting one model for all the products. Yeah, here you are just talking about when you use, for example, exponential smoothing, ARIMA, or other methods. Yeah, for the how you will do this in an automatic way. I think you can do this in an easy way. If you are using, for example, R, you can compare many methods for each product. It may take time, but I think it can. There is no problem with that.
Also, I could.
So you'd run several models and compute different error statistics for each, and then have some sort of algorithm that. Because I'm just thinking, there's no human sitting there, is there, like sifting through it?
No, I could try and answer this if you want. I mean, this kind of standard procedure or standard practice. One of the ways to decide which method you want is to run a few of them on each product. Not even so you have 10,000 products. You run, let's say, simple exponential smoothing or a simple method that doesn't look into a trend or a seasonal pattern. So you run that and you calculate some of the measures that Hikame mentioned earlier. Then you apply maybe a method with a trend, so maybe halts, and then you calculate the errors with that method. And then maybe you apply a method that has trend and seasonality, like halt winters, and then you calculate the errors with that method. So the assumption then would be that the method that if there's a seasonal pattern in a subset of the drugs, then that method, that subset of the drugs would go better with the halt winters method that takes into account the seasonal patterns. So you have 10,000 products, you automatically split them in out of sample in some way, and then in the end you look at how many of them perform better with a simple method, how many of them perform better with the other methods. And since Hikame mentioned also R, I mean, ETS as a function does that automatically for you. So basically you can run your whole data set through R with a simple ETS function and get the result I just briefly described.
Yeah, but ETS is specific to exponential smoothing. Yeah, but you don't need to distinguish between halt winters and I think I share the same point with Thanos. Yes, Chris.
Okay, cool. Yep, that sounds good.
But how many products you have, Chris? But
I don't know exactly. I would say at least 1,000. Certainly more than a human being could actually ever do. Certainly.
Yeah, but I think 1,000. I have seen tens of thousands of products. So 1,000, you can. If you use,
sure, still cannot be manually done, all of them.
Yeah,
but,
it can. Yeah, you cannot do it manually. Of course.
Yeah, one of the things that can be done, and goes back to the value-added analysis, and so some of them, the statistical algorithms would do fairly well with. Some of them they would not. And then that's one way to distinguish where you should actually spend your time on. So some like 10 maybe of the 1,000, they're expensive enough, and the forecasts are not good enough to validate you spending some time on them and using your expert knowledge, your outside information to try to improve the forecasts and the performance of those 10 drugs. For instance, if you have a drug for COVID that it's not even in the data set, then surely the statistical models will not do anything good with it. So for that specific case, you need to apply your expert knowledge, follow the news, maybe see who, like speak with your manager, speak with the doctors, and see that this is the one we need to stock now, right? So this knowledge is not in the data set. No statistical model will pick up on it. So that's and then there's automatic ways, and also this chapter touches on it, and Hikame briefly mentioned this in the fairly last bit of the presentation about tracking signals maybe, and the ranges that are acceptable in terms of errors. So you have a forecasting measure, you have a forecasting model for a product, and for 10 months it goes all right, and then for the 11th month it goes out of the bounds. So that flags it up for you, and you go and have a look at it manually.
Yeah. Okay. Cool. Right. Okay. Yeah. It's just, I mean, I've done forecasting, but I've never done it like on, in sort of. It feels a bit weird to not ever look at. I don't feel like I'm not ever looking at the actual data, am I? But yeah, that sounds practical. Yeah.